They are not supposed to exist. That is what scientists keep saying every time they find something new out there in the darkness of space. Stars that spin hundreds of times per second, invisible forces that push galaxies apart, planets made of pure diamond drifting alone in the void. The universe is full of things that break our rules, things that make us scratch our heads and wonder if we really understand anything at all. And today, we are going on a journey through the strangest discoveries we have ever made in space. If you enjoy learning about the mysteries of the cosmos, make sure to hit that like button and subscribe to the channel so you never miss another adventure into the unknown. Let us start with something that might surprise you. Most of the universe is invisible. Not invisible like air, which you cannot see but can feel. We are talking about something far stranger, something that does not interact with light at all, something that scientists call dark matter. Here is the problem that led to this discovery. When astronomers looked at galaxies spinning through space, they noticed something odd. The galaxies were spinning too fast, way too fast. According to the laws of physics, they should be flying apart. The gravity from all the stars and gas we could see was not nearly enough to hold them together. It was like watching a merry-go-round spin at full speed, with everyone somehow staying in their seats, even though they should have been thrown off long ago. So scientists asked a simple question. What if there is more stuff out there than we can see? What if there is matter that does not shine, does not glow, does not interact with light in any way? What if this invisible matter is providing the extra gravity needed to hold galaxies together? That idea became known as dark matter, and the more we look for it, the more evidence we find. We can see its effects everywhere. It bends light from distant galaxies, creating what we call gravitational lensing. It shapes the way galaxies cluster together across the cosmos. It even affects the cosmic background radiation left over from the beginning of the universe. But here is the truly strange part. We have no idea what dark matter actually is. We know it exists. We can measure its effects. We can calculate how much of it there must be. In fact, dark matter makes up about 27% of the entire universe. That is more than 5 times the amount of regular matter, the stuff that makes up you and me and stars and planets. Yet we cannot see it, touch it, or detect it directly in any experiment we have ever designed. Scientists have built massive detectors deep underground, hoping to catch a dark matter particle bumping into regular atoms. They have searched for signs of dark matter at particle colliders like the Large Hadron Collider. They have looked for gamma rays that might be produced when dark matter particles collide with each other. So far, nothing. Dark matter remains completely invisible, completely mysterious, and completely essential to understanding how the universe works. But dark matter is only part of the invisible universe. There is something even stranger out there, something that makes up about 68% of everything that exists, something called dark energy. To understand dark energy, we need to go back to the 1920s, when an astronomer named Edwin Hubble made one of the most important discoveries in history. He found that the universe is expanding. Galaxies are moving away from each other, and the farther away a galaxy is, the faster it seems to be receding. The universe is not static. It is growing larger every moment. Now, this expansion made sense in a way. The Big Bang created a tremendous burst of energy that sent everything flying outward. You might expect that over time, gravity would slow this expansion down. All that matter pulling on itself should act like a brake, gradually reducing the speed at which galaxies drift apart. But in 1998, 2 teams of scientists discovered something that turned our understanding of the universe upside down. They were studying distant supernovas, massive star explosions that shine so brightly we can see them across billions of light years. By measuring these supernovas, they could figure out how fast the universe was expanding at different points in cosmic history. What they found shocked everyone. The expansion of the universe is not slowing down. It is speeding up. Something is pushing galaxies apart faster and faster, fighting against gravity, accelerating the growth of the cosmos. This mysterious force got a name: dark energy. And here is where things get really weird. Dark energy does not act like anything we understand. It is not matter. It does not clump together like dark matter does. It seems to be a property of space itself, filling every corner of the universe with a constant, steady push outward. The more space expands, the more dark energy there is, and the faster the expansion accelerates. Some scientists think dark energy might be what Einstein called the cosmological constant, a built-in feature of space-time that causes it to expand. Others think it might be a new kind of energy field that permeates the universe. Some even wonder if dark energy is slowly changing over time, which would have huge implications for the ultimate fate of the cosmos. If dark energy keeps accelerating the expansion forever, eventually galaxies will drift so far apart that light from one will never reach another. The universe will become cold, dark, and empty. Stars will burn out. Black holes will evaporate. Everything will spread out into a thin, lifeless soup of particles, separated by distances so vast that nothing will ever interact with anything else again. But we do not know for sure if that will happen. We do not know what dark energy really is. We do not know why it exists or how it works. All we know is that it makes up more than 2/3 of everything in the universe. And we are completely in the dark about what it actually is. Think about that for a moment. When you add up dark matter and dark energy, you get about 95% of the universe. That means everything we can see, every star, every planet, every galaxy, every nebula, every atom in your body makes up only about 5% of what exists. The rest is invisible, mysterious, and waiting to be understood. Now, let us leave the invisible universe behind and talk about some of the strangest objects we can actually see. Let us talk about neutron stars. When a massive star dies, it can explode in a supernova, one of the most powerful events in the universe. But what happens to the core of that star? If the star is big enough, the core collapses into a black hole. But if the star is not quite that massive, something else happens. The core gets crushed down into an incredibly dense ball of neutrons. A neutron star. How dense are we talking? Imagine taking the mass of our Sun, which is already 330,000 times the mass of Earth, and squeezing it into a ball about 12 miles across. That is roughly the size of a city. A single teaspoon of neutron star material would weigh about 6 billion tons. That is more than every car, truck, and building on Earth combined, packed into a space smaller than your thumb. Neutron stars are so dense that their gravity warps space-time in extreme ways. If you could stand on the surface of a neutron star, which you absolutely could not survive, you would be crushed instantly by gravity about 2 billion times stronger than Earth's. Light itself bends around these objects, allowing you to see parts of the star that should be hidden behind the curve of its surface. But neutron stars get even stranger. Some of them spin incredibly fast. These spinning neutron stars are called pulsars, and they emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like the light from a lighthouse. If Earth happens to be in the path of one of these beams, we see regular pulses of radiation, hence the name pulsar. Some pulsars spin slowly, taking seconds to complete a rotation, but others spin so fast it seems impossible. The fastest known pulsar spins over 700 times per second. That means a point on its equator is moving at a significant fraction of the speed of light. These millisecond pulsars are some of the most precise clocks in the universe, ticking with a regularity that rivals the best atomic clocks on Earth. Scientists use pulsars to study all sorts of things. By carefully timing the pulses, astronomers can detect tiny wobbles caused by orbiting planets, measure the warping of space-time predicted by Einstein, and even search for gravitational waves rippling through the cosmos. Pulsars are like cosmic lighthouses and precision instruments all rolled into one. But there is a type of neutron star that makes ordinary pulsars look tame. They are called magnetars, and they have the strongest magnetic fields in the known universe. How strong are we talking? The magnetic field of a typical refrigerator magnet is about 5 millitesla. The magnetic field of an MRI machine, strong enough to affect atoms in your body, is about 3,000 millitesla. The magnetic field of a magnetar can reach up to 100 billion millitesla. That is 1 trillion times stronger than a refrigerator magnet. A magnetar's magnetic field is so powerful it could erase every credit card on Earth from a distance of halfway across the solar system. If you somehow got within 1,000 miles of a magnetar, the magnetic field would tear apart the atoms in your body, disrupting the very chemistry of life. Even from much farther away, the field would pull on the iron in your blood and the electrons in your tissues. Magnetars are also incredibly violent. They experience starquakes, where the crust of the neutron star cracks and shifts. These quakes release enormous bursts of energy. In 2004, a magnetar located about 50,000 light-years away released a burst of gamma rays so powerful it actually affected Earth's atmosphere. Think about that. An event happening on the other side of our galaxy was energetic enough to disturb the air above your head. We do not fully understand how magnetars form or why their magnetic fields are so strong. Some scientists think it has to do with how the neutron star spins when it first collapses, creating a kind of cosmic dynamo effect. Others think exotic physics inside the ultra-dense core might play a role. What we do know is that magnetars are among the most extreme objects in the universe, and they challenge our understanding of physics in fundamental ways. Now let us talk about stars that do something even more surprising than spinning fast or having strong magnetic fields. Let us talk about stars that get kicked out of their own galaxies. They are called hypervelocity stars, and they are racing through space at speeds that seem impossible. Most stars in our galaxy orbit the center at a few hundred kilometers per second. Hypervelocity stars move at over 1,000 kilometers per second. Some have been clocked at nearly 2,000 kilometers per second. That is fast enough to escape the gravitational pull of the entire Milky Way galaxy. How does a star end up moving that fast? The most likely explanation involves the supermassive black hole at the center of our galaxy. When a binary star system, two stars orbiting each other, passes too close to this black hole, something dramatic can happen. The intense gravity can rip the pair apart, capturing one star and flinging the other outward at tremendous speed. It is like a cosmic slingshot, using the most powerful gravitational source in the galaxy to accelerate a star to escape velocity. Astronomers have discovered dozens of hypervelocity stars in and around our galaxy. Some are heading out into intergalactic space, destined to drift alone between galaxies for eternity. Others might be caught by the gravity of nearby galaxies and eventually settle into new orbits far from home. Imagine being a planet around one of these hypervelocity stars. One moment you are part of a normal stellar system, orbiting through the galaxy like billions of others. The next moment, your star has been flung into the void, carrying you along on a journey to nowhere, leaving behind the familiar glow of the Milky Way as it slowly shrinks into a distant smudge of light. Hypervelocity stars tell us something important about the extreme environments near supermassive black holes. They also give us a way to measure the mass of our galaxy. By tracking how fast these stars are moving and calculating what it takes to escape the Milky Way's gravity, scientists can figure out how much total matter our galaxy contains, including all that invisible dark matter we talked about earlier. Speaking of mysterious stars, there is one star in particular that captured the world's imagination. It is called Tabby's star, officially known as KIC 8462852, and for a while, some people thought it might be surrounded by alien megastructures. The story began in 2015, when citizen scientists participating in a project called Planet Hunters noticed something strange in data from the Kepler Space Telescope. Kepler was designed to find planets by watching for tiny dips in starlight that occur when a planet passes in front of its host star. These dips are usually small and regular, happening like clockwork as the planet completes its orbit. But Tabby's star was different. Its light was dimming in ways that made no sense. Sometimes the brightness dropped by a fraction of a percent. Other times it dropped by more than 20%. The dimming events were not regular or predictable. They came at odd intervals, lasted different amounts of time, and varied wildly in how much light they blocked. This was not like any planet astronomers had ever seen. Even a massive planet like Jupiter only blocks about 1% of its star's light. What could be blocking 20% or more? And why would it happen so irregularly? Some scientists proposed that a swarm of comets might be passing in front of the star, breaking up and creating irregular clouds of debris. Others suggested the star might be surrounded by a disk of dust and gas from a recent planetary collision. But these explanations had problems. The dimming events were too deep, too irregular, and too hard to explain with normal astronomical processes. Then someone proposed a more exotic idea. What if an advanced alien civilization had built massive structures around the star to capture its energy? These hypothetical megastructures, sometimes called Dyson spheres or Dyson swarms, had been proposed by physicist Freeman Dyson back in 1960 as something a highly advanced civilization might build. Could Tabby's star be evidence of alien engineering? The idea caught fire in the media. Headlines screamed about alien megastructures and mysterious signals from deep space. Astronomers rushed to study the star with every instrument they could find. Radio telescopes listened for artificial signals. Optical telescopes watched for patterns in the dimming. The search for extraterrestrial intelligence, or SETI, turned its attention to this peculiar patch of sky. What did they find? No aliens. At least, no evidence of aliens. Instead, more detailed observations revealed that the dimming was caused by fine dust particles, not large solid structures. When light at different wavelengths was analyzed, scientists found that shorter wavelengths were blocked more than longer ones, which is what you would expect from tiny dust grains. A solid megastructure would block all wavelengths equally. The best current explanation is that Tabby's star is surrounded by an uneven cloud of dust, possibly from comets that were gravitationally disturbed and passed close to the star, releasing debris. It is still a strange and unusual star, worthy of continued study, but it probably is not home to an advanced alien civilization. Still, The excitement around Tabby's star reminds us of something important. We are always looking, always searching, always hoping to find signs that we are not alone in the universe. Every strange signal, every unexplained phenomenon, every mystery that defies easy explanation gets our attention. Because somewhere out there, maybe around a star we have not studied yet, there might be something truly extraordinary waiting to be found. Now let us shift our attention from stars to the monsters that lurk at the hearts of galaxies. Let us talk about black holes and some of their most bizarre relatives. Black holes are places where gravity has won completely. When a massive star collapses or when matter gets compressed beyond a certain point, it creates a region of space where the gravitational pull is so strong that nothing, not even light, can escape. The boundary around a black hole, beyond which nothing can return, is called the event horizon. Cross that line, and you are gone forever. Black holes come in different sizes. Stellar mass black holes form from the deaths of massive stars, and typically have masses ranging from a few times to a few dozen times the mass of our Sun. But at the centers of galaxies, including our own Milky Way, lurk supermassive black holes. These giants can have masses of millions or even billions of suns. When matter falls toward a supermassive black hole, it does not just drop straight in. Instead, it spirals around, forming a disk of material called an accretion disk. As gas and dust in this disk swirl faster and faster, they heat up to millions of degrees. This superheated material glows incredibly bright, outshining entire galaxies. When a supermassive black hole is actively feeding like this, we call it a quasar. And quasars are among the brightest objects in the entire universe. The first quasars were discovered in the 1960s, and they puzzled astronomers for years. They looked like stars, just points of light in the sky. But their spectra, the patterns of light they emitted, were like nothing anyone had seen before. The light was shifted toward the red end of the spectrum by enormous amounts, indicating that these objects were incredibly far away. How far? The most distant quasars we have found are so far away that their light has been traveling toward us for more than 13 billion years. We are seeing them as they were when the universe was less than 1 billion years old. And despite being so far away, they are bright enough for us to see them clearly. For a quasar to be visible from 13 billion light-years away, it has to be putting out an almost unimaginable amount of energy. We are talking about hundreds of times more energy than an entire galaxy of stars. And all of that energy is coming from a region smaller than our solar system, from the violent maelstrom of matter spiraling into a supermassive black hole. Quasars teach us about the early universe. They show us that supermassive black holes formed surprisingly quickly after the Big Bang, though we are still not entirely sure how. They act as cosmic beacons, illuminating the gas and dust between us and them, allowing astronomers to study material that would otherwise be invisible. And they demonstrate the incredible power that gravity can unleash when enough matter comes together. But black holes do not always stay put at the centers of galaxies. Sometimes they wander. Rogue black holes are black holes that have been kicked out of their galaxies or that never belonged to a galaxy in the first place. They drift through intergalactic space, invisible and undetectable, except by the gravitational effects they have on nearby matter. How does a black hole go rogue? One way is through gravitational waves. When two supermassive black holes merge, they can release a burst of gravitational waves that carries momentum. If this burst is asymmetric, it can kick the newly formed black hole in one direction, sometimes hard enough to send it flying out of its galaxy entirely. Computer simulations suggest that this kick can reach speeds of thousands of kilometers per second. Another way rogue black holes might form is in the early universe, when smaller galaxies were merging to form larger ones. The chaotic gravitational interactions during these mergers could have ejected some black holes into the void between galaxies. We have found some candidates for rogue black holes, though confirming them is difficult. One method is to look for stars that are orbiting nothing visible, their motions suggesting a massive invisible companion. Another is to watch for gravitational lensing events, where the gravity of an unseen black hole bends the light from a more distant object. The thought of invisible black holes wandering through space is a little unsettling. Could one drift into our solar system? Technically, yes, but the chances are incredibly small. Space is so vast and black holes are so rare that the odds of one passing close enough to affect us are essentially zero. Still, the existence of rogue black holes adds to the sense that the universe is a wild and unpredictable place. Now let us talk about something even more mysterious than individual black holes. Let us talk about the Great Attractor. Imagine you are floating in space, watching the galaxies around you. Everything seems to be moving, drifting apart as the universe expands. But as you watch more carefully, you notice something strange. All the galaxies in your region of space, including the Milky Way, seem to be moving in a particular direction. Not just expanding, but actually flowing toward a specific point in the sky. This is what astronomers discovered when they mapped the motions of galaxies in our cosmic neighborhood. We are not just expanding with the universe. We are also falling toward something incredibly massive, something hidden behind the dense band of stars that makes up the center of our own galaxy, blocking our view. Scientists call this hidden mass concentration the Great Attractor. It is located about 250 million light-years away, in the direction of the constellations Centaurus and Hydra, and it is pulling on galaxies across a vast region of space, influencing the motions of thousands of galaxies, including our own. What is the Great Attractor? For decades, astronomers could not see it clearly because our own Milky Way was in the way. The zone of avoidance, as it is called, blocks about 20% of the sky with dust and stars that prevent us from seeing what lies beyond. But using X-ray telescopes and radio telescopes, which can peer through the dust better than visible light telescopes, scientists have gotten a better look. The Great Attractor turns out to be associated with a massive supercluster of galaxies called the Norma Cluster, also known as Arbel 3627. This cluster, along with other nearby structures, creates an enormous gravitational well that is drawing matter toward it. But even the Great Attractor is not the end of the story. Recent research has revealed an even larger structure called Laniakea, a supercluster of superclusters that includes the Great Attractor and extends across more than 500 million light-years. Our Milky Way is just one tiny galaxy among thousands in this vast cosmic watershed, all flowing toward a common gravitational center. And beyond Laniakea, there are even larger structures being discovered. The universe is not smooth. It is lumpy, with matter concentrated in walls, filaments, and clusters, separated by enormous voids of almost empty space. Understanding these structures, how they formed and how they evolve, is one of the great challenges of modern cosmology. Speaking of voids, let us take a moment to talk about the emptiest places in the universe. Cosmic voids are exactly what they sound like, huge regions of space where almost nothing exists. No galaxies, no clusters, just empty darkness stretching for hundreds of millions of light years. These voids are not completely empty, of course. There might be a few lonely galaxies scattered here and there, some gas and dark matter. But compared to the crowded regions where galaxies cluster together, voids are practically deserted. They make up most of the volume of the universe, while nearly all the matter is concentrated in the thin walls and filaments that separate them. The largest known void is called the Bootes void, discovered in 1981. It spans about 330 million light-years across. To put that in perspective, our entire Milky Way galaxy is about 100,000 light-years across. You could fit thousands of Milky Ways inside the Bootes void, and it would still look empty. When astronomers first discovered the Bootes void, they were surprised to find so few galaxies inside it. They counted only about 60 galaxies in a region where they expected to find around 2,000. Why is this region so empty? What happened to prevent galaxies from forming here? The answer likely goes back to the earliest moments after the Big Bang. Small differences in the density of matter in the early universe got amplified over billions of years. Regions that were slightly denser attracted more matter through gravity, eventually forming the galaxies and clusters we see today. Regions that were slightly less dense lost matter to their neighbors, becoming the voids. But cosmic voids are not just empty curiosities. They tell us important things about how the universe evolved. By studying the size and distribution of voids, scientists can test their models of cosmic structure formation. Voids also provide a relatively clean environment to study dark energy, since there is less matter to complicate the picture. Some scientists have even proposed that living in a cosmic void could explain certain puzzling observations about the universe. What if our local region of space is slightly emptier than average? Could that affect how we measure the expansion of the universe? It is an intriguing idea, though most evidence suggests we live in a fairly typical part of the cosmos. Now let us leave the giant structures of the universe and zoom in on something smaller, but no less strange. Let us talk about weird planets. We used to think that planets came in a few basic types. Rocky planets like Earth, Mars, and Venus. Gas giants like Jupiter and Saturn. Ice giants like Uranus and Neptune. Our solar system seemed to offer a nice, orderly menu of planetary options. Then we started finding planets around other stars, exoplanets as they are called, and suddenly our neat categories fell apart. The universe, it turns out, has a much wilder imagination than we ever suspected. Take diamond planets, for example. Scientists have theorized that certain carbon-rich planets could have interiors made largely of diamond. The pressures and temperatures deep inside these worlds would squeeze carbon into its crystalline form, creating layers of diamond hundreds of miles thick. One candidate for a diamond planet is 55 Cancri e, a super-Earth orbiting close to its star about 40 light-years away. This planet is about twice the diameter of Earth and about 8 times as massive. Based on its density and the composition of its host star, some scientists believe 55 Cancri A might have a diamond interior worth more money than exists in the entire human economy. Not that we could ever get to it or mine it, but 55 Cancri E is strange for other reasons too. It orbits so close to its star that a year there lasts only 18 hours. The surface temperature on the day side reaches over 2,000 degrees Celsius, hot enough to melt most metals. Recent observations suggest the planet might have a thick atmosphere with possible volcanic activity, creating a hellish environment that challenges our understanding of how rocky planets work. Then there are planets that rain strange things. On Earth, we have water rain and occasionally hail or snow. But on some exoplanets, the weather is far more exotic. Take HD 189733b, sometimes nicknamed the Deep Blue Planet. This gas giant orbits close to its star and has a striking cobalt blue color. But that blue is not from water like Earth's oceans. It comes from silicate particles in the atmosphere, essentially tiny glass droplets. And when it rains on HD 189733b, it rains glass, sideways. The winds on this planet reach over 7,000 kilometers per hour, blowing the glass rain horizontally across the sky. Or consider WASP 76b, where astronomers have detected iron in the atmosphere. This planet is so hot that iron vaporizes on the daytime side. The iron vapor gets carried by winds to the cooler nighttime side, where it condenses and falls as iron rain. Imagine standing on a world where the clouds are made of metal vapor and the rain is liquid iron. These extreme weather patterns exist because many exoplanets orbit incredibly close to their stars, becoming tidally locked with one side always facing the star and one side always facing away. The temperature difference between day and night can be thousands of degrees, driving violent atmospheric circulation that creates weather unlike anything in our solar system. But perhaps the strangest planets of all are the ones that have no star at all. Rogue planets. A rogue planet is a world that drifts through interstellar space, unbound to any star. It might have formed around a star and then been ejected through gravitational interactions with other planets. Or it might have formed independently, collapsing from a small cloud of gas and dust that was not quite massive enough to become a star. We do not know exactly how many rogue planets are out there, but some estimates suggest there could be billions of them in our galaxy alone. Maybe even more rogue planets than there are stars. They drift in the darkness between solar systems, too cold and too far from any light source for us to see them easily. The surfaces of most rogue planets would be frozen solid, locked in permanent darkness with temperatures near absolute zero. Any atmosphere would have long since frozen onto the surface. At first glance, they seem like the least hospitable places imaginable. But here is a surprising thought. Some rogue planets might actually be warm enough for liquid water. How? If a rogue planet has a thick hydrogen atmosphere, the atmospheric pressure could create a greenhouse effect strong enough to trap heat from the planet's interior. Many planets generate their own heat through radioactive decay in their cores. With enough insulation from a dense atmosphere, a rogue planet might maintain a liquid ocean beneath its frozen surface, or even on its surface in the warmest regions. Could life exist on a rogue planet? It seems unlikely given the lack of sunlight for photosynthesis. But life on Earth has been found in deep sea vents far from any sunlight, surviving on chemical energy from the planet's interior. Perhaps something similar could happen on a rogue planet drifting through the eternal night. The thought is both fascinating and a little eerie. Imagine an entire planet full of life, never knowing the light of a star, evolving in complete darkness, perhaps never even developing the concept of a sun because there has never been one in their sky. Their universe would be utterly alien to us. Now let us talk about something that connects all these strange objects and places, the very fabric of the universe itself. Let us talk about the cosmic microwave background radiation, the oldest light in existence. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that moment, the cosmos was a hot, dense soup of particles and radiation, so thick that light could not travel far without hitting something. But when atoms formed, suddenly the universe became transparent. Light could finally travel freely across space. That light has been traveling ever since. Over billions of years, the expansion of the universe has stretched it from visible light into microwaves. Today, we can detect it, coming from every direction in the sky, a faint glow that fills all of space. This is the cosmic microwave background, or CMB. The CMB is remarkably uniform. No matter which direction you look, the temperature is almost exactly the same, about 2.7 degrees above absolute zero. This tells us that the early universe was incredibly smooth, with matter and energy distributed almost evenly across space. But the key word is almost. When we look very closely at the CMB, we see tiny fluctuations in temperature. Some spots are slightly warmer, some slightly cooler, differing by only about 1 part in 100,000. These tiny differences are the seeds of all the structure we see today. The slightly denser regions had slightly stronger gravity, pulling in more matter over time, eventually forming galaxies, stars, and planets. The CMB is like a baby picture of the universe. It shows us what the cosmos looked like when it was only 380,000 years old, long before any stars or galaxies existed. By studying the patterns in this ancient light, scientists can figure out fundamental properties of the universe, its age, its composition, its geometry, and its fate. But there are some puzzles in the CMB that we do not fully understand. One of the strangest is the CMB cold spot. In the constellation Eridanus, there is a region of the CMB that is noticeably colder than anywhere else. It is about 1.8 billion light-years across and about 70 microkelvins cooler than the average temperature of the CMB. That might not sound like much, but given how uniform the CMB usually is, this cold spot stands out like a sore thumb. What could cause such a large cold region? One explanation involves a supervoid, an unusually large cosmic void in the direction of the cold spot. When CMB light passes through a void, it loses a tiny bit of energy due to the expansion of the universe. A really big void could cause the light to lose enough energy to create a cold spot. And there is indeed a supervoid in roughly the right place. But some calculations suggest it is not quite big enough or empty enough to fully explain the cold spot. Something else might be going on. Some more exotic explanations have been proposed. Maybe the cold spot is evidence of a collision with another universe in the very early cosmos. In some theories of inflation, the rapid expansion that occurred just after the Big Bang, our universe might have bumped into neighboring bubble universes. A collision like that could have left an imprint on the CMB. Or maybe the cold spot is just a statistical fluke, an unlikely but not impossible random variation. With a whole sky full of CMB data to analyze, we might expect to find at least one region that looks unusually cold, just by chance. The truth is, we do not know for sure what causes the CMB cold spot. It remains one of the many mysteries of cosmology, a puzzle that might one day reveal something profound about the nature of the universe. Now let us move on to another category of cosmic mysteries: the transient events that flare up without warning and then disappear. Let us talk about fast radio bursts. A fast radio burst, or FRB, is exactly what it sounds like. A burst of radio waves that lasts only a few milliseconds. That is shorter than the blink of an eye. And yet, in that tiny fraction of a second, an FRB releases as much energy as our sun puts out in an entire day. The first FRB was discovered in 2007, found in archival data from a telescope in Australia. At first, scientists were not sure what to make of it. Was it a glitch in the equipment? A local source of interference? Something from Earth being picked up by mistake? But as more telescopes around the world searched for these signals, more FRBs turned up. They were coming from all over the sky. They were extremely bright but extremely brief. And based on how their radio waves were spread out, they seemed to be coming from very far away, billions of light years in some cases. The mystery deepened when astronomers discovered that some FRBs repeat. Most appear to be one-time events, flashing once and never again. But a few sources produce multiple bursts, sometimes dozens of them, separated by days or weeks or months. This ruled out some explanations, like the collision of two neutron stars, which would be a one-time event. Whatever was causing the repeating FRBs had to survive the process. Scientists have proposed many explanations for FRBs. Magnetars are a leading candidate, since we know they can produce powerful bursts of radiation. In fact, in 2020, a magnetar in our own galaxy was caught producing an FRB-like burst, providing the first direct evidence linking magnetars to, at least some FRBs. But magnetars might not explain all FRBs. The energy and patterns of some bursts suggest there might be multiple types of sources. Some FRBs might come from the interactions between neutron stars and their environments. Others might involve exotic physics we do not yet understand. One of the most exciting things about FRBs is that they can be used as tools to study the universe. As the radio waves travel through space, they interact with the electrons in the thin gas between galaxies. By measuring how much the waves are affected, astronomers can count up all the matter along the line of sight. This helps solve the missing baryon problem, the puzzle of where all the normal matter in the universe is hiding. FRBs have shown us that much of the universe's ordinary matter is spread out in the vast spaces between galaxies, too thin and cool to be detected by other means. Every FRB we detect is like a flashlight beam illuminating the cosmic web, revealing structure that would otherwise be invisible. We are still in the early days of FRB science. New telescopes designed specifically to detect these bursts are coming online, and the number of known FRBs is growing rapidly. Whatever secrets they hold, we are just beginning to unlock them. Now, let us talk about an even more violent category of cosmic event: gamma-ray bursts. If FRBs are mysterious, gamma-ray bursts are terrifying. They are the most energetic explosions in the universe, releasing more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. If a gamma-ray burst happened anywhere near Earth, it would be catastrophic. Gamma-ray bursts were first detected in the 1960s by military satellites designed to monitor nuclear weapons tests. The satellites kept detecting powerful bursts of gamma rays coming from space, nothing like any nuclear explosion. For years, the bursts remained a complete mystery. They came from random directions, lasted random amounts of time, and then disappeared. Eventually, astronomers realized there were two main types of gamma-ray bursts. Long bursts last more than 2 seconds and seem to come from the deaths of very massive stars. When these stars collapse, they form black holes surrounded by rapidly spinning disks of material. Jets of energy shoot out along the poles of this disk at nearly the speed of light. If one of these jets happens to point toward Earth, we see a gamma-ray burst. Short bursts last less than 2 seconds and have a different origin. They seem to come from the mergers of neutron stars, when two of these ultra-dense objects spiral together and collide. This was confirmed in 2017, when astronomers detected both a gravitational wave signal and a short gamma-ray burst from the same event, proving that neutron star mergers produce these bursts. The energy involved in gamma-ray bursts is hard to comprehend. In a few seconds, a gamma-ray burst can release as much energy as trillions of nuclear bombs. The gamma rays are so intense that if a burst happened within a few thousand light years of Earth, It could strip away our ozone layer and trigger a mass extinction. Some scientists have speculated that a gamma-ray burst might have caused mass extinctions in Earth's past. The late Ordovician extinction, about 450 million years ago, wiped out most marine life. Some researchers think a gamma-ray burst could have been responsible, though this remains speculative. The good news is that gamma-ray bursts are rare and the universe is big. The chances of one happening close enough to threaten Earth are extremely small, but they remind us that the cosmos is not always a peaceful place. Immense violence can erupt without warning, releasing energies that dwarf anything in human experience. Let us take a step back now and think about what all these strange discoveries mean. Every one of these phenomena, dark matter, dark energy, pulsars, magnetars, hypervelocity stars, black holes, quasars, rogue planets, diamond worlds, cosmic voids, the CMB, fast radio bursts, gamma-ray bursts, every single one of them was completely unknown to humans just a few generations ago. Our grandparents grew up in a world where the Milky Way was thought to be the entire universe. Our great-grandparents lived before anyone knew that atoms existed. Go back a few more generations, and people thought the Earth was the center of creation, that the stars were lights fixed to a celestial sphere, that the cosmos was small and orderly and made just for us. Now we know better. The universe is vast beyond comprehension. It is full of things that make no sense by the standards of everyday experience. It operates according to rules that seem designed to confuse and amaze us. And we have discovered all of this in the blink of an eye, cosmically speaking. What will we discover next? What strange new phenomena are waiting, out there, just beyond the reach of our current telescopes and instruments? History teaches us that whenever we develop new ways of looking at the universe, we find things we never expected. Radio telescopes revealed quasars and pulsars. X-ray telescopes showed us black holes feeding on gas. Gravitational wave detectors opened a completely new window on the cosmos. Each new window has brought surprises. Each new technology has revealed that the universe is stranger than we imagined. There is every reason to think this pattern will continue. Let us go deeper into some of these mysteries and explore the details that make them so fascinating. Let us return to the topic of black holes, because there is so much more to say about these cosmic enigmas. We talked earlier about how black holes form and how they can power quasars. But there are aspects of black holes that push our understanding of physics to its breaking point. Consider what happens at the very center of a black hole. General relativity, Einstein's theory of gravity, predicts that all the mass of a black hole gets crushed down to a single point of infinite density, called a singularity. At this point, space and time themselves break down. The equations that describe physics everywhere else in the universe simply stop working. Most physicists believe that singularities are not real physical things, but rather signs that our theory is incomplete. General relativity does not account for quantum mechanics, the physics of very small things. When you try to describe a singularity, you are dealing with something that is both incredibly massive and incredibly small. The exact situation where gravity and quantum mechanics should both be important. We do not have a theory of quantum gravity yet. Developing one is one of the great unsolved problems in physics. But whatever form it takes, a theory of quantum gravity should tell us what really happens at the center of a black hole. Maybe singularities get smoothed out into something less extreme. Maybe space-time bounces back and connects to somewhere else. Maybe there is something completely unexpected that we cannot even imagine yet. Speaking of unexpected things inside black holes, There is a famous thought experiment called the black hole information paradox. It goes like this. Quantum mechanics says that information cannot be destroyed. If you know the exact state of a system at one moment, you can in principle calculate what it was in the past and what it will be in the future. Information is preserved, but black holes seem to destroy information. If you throw a book into a black hole, all the information in that book falls past the event horizon and becomes inaccessible. The only things you can measure about the black hole from outside are its mass, its spin, and its electric charge. Everything else about what fell in is lost. This gets worse. Stephen Hawking showed in the 1970s that black holes slowly leak energy through a process now called Hawking radiation. Over incredibly long time scales, black holes evaporate. When a black hole finally evaporates completely, what happens to all the information that fell into it? Does it vanish from the universe, violating quantum mechanics? Or does it somehow come out in the Hawking radiation in a way we do not understand? This paradox has puzzled physicists for decades. Various solutions have been proposed. Maybe information is encoded in the Hawking radiation in subtle ways. Maybe there is something wrong with our understanding of what happens at the event horizon. Maybe the laws of physics work differently than we think. Recent work suggests that information might indeed escape from black holes, encoded in quantum correlations in the radiation. But the details are still being worked out. The black hole information paradox remains one of the deepest puzzles in theoretical physics, touching on the nature of space, time, gravity, and quantum reality. There is another strange property of black holes that deserves mention: time dilation. Near a black hole, time passes more slowly than it does far away. This is not science fiction. It is a real, measured effect predicted by general relativity. The stronger the gravitational field, the slower time flows. If you could somehow hover just above the event horizon of a black hole, time for you would nearly stop relative to someone far away. An hour for you might be years or decades or centuries for them. And if you could survive the trip and come back, you would find that the universe had aged while you barely changed. This effect gets more extreme the closer you get to the black hole. Right at the event horizon, from an outside perspective, time seems to stop completely. That is why anything falling into a black hole appears to freeze at the horizon, getting dimmer and dimmer, but never quite crossing. In the infalling object's own frame of reference, though, it crosses the horizon in finite time and falls toward the singularity. These mind-bending effects of time near black holes have inspired countless science fiction stories, but they are real physics. Time is not absolute. It flows at different rates depending on gravity and motion. Black holes are just the most extreme example of something that happens everywhere, all the time, throughout the universe. Let us shift gears and talk about another category of strange cosmic objects: the exotic matter that might exist under extreme conditions. Under normal conditions, matter is made of atoms, which are made of protons, neutrons, and electrons. But in extreme environments like the cores of neutron stars, matter can take on bizarre forms. In a neutron star, the pressure is so high that protons and electrons are squeezed together to form neutrons. The entire star becomes essentially one giant atomic nucleus, made almost entirely of neutrons packed together. This neutron matter is incredibly dense and has properties unlike anything we can create on Earth. But some theorists think there might be something even stranger inside neutron stars. At even higher pressures, the neutrons themselves might break down into their component quarks. Quarks are the fundamental particles that make up protons and neutrons. Under normal conditions, quarks are always bound together in groups of 2 or 3. But in the extreme environment of a neutron star core, they might roam freely as a quark gluon plasma. If this happens, the result would be a quark star, an object even denser and more extreme than a neutron star. Some neutron stars behave in ways that suggest they might have quark cores, but we have not confirmed this yet. The physics of ultra-dense matter is hard to study because we cannot recreate these conditions in laboratories. There is an even more exotic possibility called strange matter. This would be matter containing strange quarks, a heavier variety of quark that normally only exists briefly in particle accelerators. Some theorists have suggested that strange matter might be more stable than ordinary matter. If that is true, then neutron stars might eventually convert into strange stars made entirely of strange matter. The idea of strange matter has inspired some alarming speculation. If strange matter is more stable than ordinary matter, what would happen if a piece of it touched ordinary matter? Would it convert everything it touched into strange matter, like some kind of cosmic infection? This scenario, sometimes called a Strangelove disaster, has been proposed as a potential danger from high-energy particle collisions, though most physicists consider it extremely unlikely. These exotic forms of matter remind us that the periodic table we learn in school is just the beginning. Under extreme conditions, matter can take on forms that have no analog in everyday experience. The universe is a laboratory that creates conditions we can barely imagine, and the results are materials and objects that challenge our understanding of physics. Let us talk about another extreme phenomenon, the fastest things in the universe. We know that nothing can travel faster than the speed of light. This is not just a practical limitation, but a fundamental law of physics. As an object approaches the speed of light, it requires more and more energy to accelerate. To actually reach the speed of light would require infinite energy, which is why it is impossible for anything with mass. But some things in the universe come remarkably close to the speed of light. We already mentioned the material in quasar jets, accelerated to near light speed by the tremendous energies near supermassive black holes. These jets can stretch for thousands of light years, plowing through intergalactic space at velocities that differ from the speed of light by only a fraction of a percent. Cosmic rays are another example. These are not really rays at all, but particles, protons, electrons, and atomic nuclei that zip through space at incredible speeds. Most cosmic rays move at a significant fraction of light speed, but the most energetic cosmic rays, called ultra-high-energy cosmic rays, have been detected with energies that are almost incomprehensible. The most energetic cosmic ray ever detected, nicknamed the Oh My God particle, was recorded in 1991. It was moving so fast that it carried about the same kinetic energy as a baseball thrown at 90 miles per hour, except it was a single subatomic particle. It was traveling so close to the speed of light that in a race with a light beam across the entire observable universe, it would lose by only about half an inch. Where do these ultra-high energy cosmic rays come from? We are not entirely sure. Something out there is accelerating particles to energies that no particle accelerator on Earth can match. Possible sources include the jets of active galactic nuclei, the blast waves from supernovas, and the collisions of galaxy clusters. These natural particle accelerators dwarf anything humans have built. Another phenomenon that approaches the speed of light is the expansion of space itself. Now, this requires some careful explanation because nothing is really moving faster than light. When we say the universe is expanding, we do not mean that galaxies are rushing through space like cars on a highway. We mean that space itself is stretching. The distance between galaxies is growing because there is more space between them, not because they are traveling through space. Because of this expansion, very distant galaxies appear to be receding from us at speeds greater than the speed of light. This is allowed because it is not motion through space but the expansion of space itself. These galaxies are not violating the speed limit. They are just being carried along by the stretching of the cosmos. The most distant galaxies we can see are receding at about 3 times the speed of light. And there are galaxies even farther away that we can never see, because their light will never be able to cross the expanding space between us. They are beyond our cosmic horizon, forever inaccessible. This brings up a humbling thought. The observable universe, everything we can see with even the most powerful telescopes, is just a fraction of what might exist. There could be entire regions of the cosmos, perhaps infinitely large, that we can never observe or interact with. The true size and extent of reality might be beyond anything we can measure or comprehend. Let us now explore some of the strangest signals we have received from space. Signals that for a while seemed like they might be from intelligent civilizations. When pulsars were first discovered in 1967, the regular, repeating pulses were so precise that the astronomers who found them half-jokingly called the first source LGM-1 for little green men. The idea that it might be an artificial signal from aliens was briefly considered before the natural explanation of spinning neutron stars was understood. But the search for extraterrestrial intelligence, or SETI, continues to this day. Scientists scan the skies with radio telescopes, looking for signals that might indicate the presence of intelligent life elsewhere in the universe. In 1977, a SETI project at Ohio State University detected a strong narrow-band radio signal that stood out dramatically from the background noise. The astronomer who found it wrote "wow" in the margin of the computer printout, and the "wow" signal has puzzled researchers ever since. The signal had many of the characteristics you would expect from an artificial extraterrestrial transmission. It was at a frequency associated with hydrogen, which SETI researchers consider a natural choice for interstellar communication. It came from the direction of the constellation Sagittarius. It was unusually strong and narrowband, unlike natural radio sources which tend to be broadband. But the "wow" signal was never detected again. Despite repeated attempts to find it, the source has remained silent. This is problematic because a genuine extraterrestrial signal should be verifiable. We should be able to point our telescopes at the same spot and detect it again. Various explanations have been proposed. Maybe it was a reflection of a human signal off space debris. Maybe it was an unusual natural phenomenon we do not understand. Maybe it was a brief transmission from a civilization that has since gone silent, or that was only briefly aimed in our direction. In 2017, a new explanation was proposed. 2 researchers suggested that the signal might have come from hydrogen clouds surrounding comets. At the time of the signal, 2 comets were in the right part of the sky, and hydrogen from their comae could potentially produce a signal like what was observed. This remains controversial, but it shows how difficult it is to identify unusual signals with certainty. The search for extraterrestrial intelligence raises profound questions. Are we alone in the universe? If not, why have we not found clear evidence of other civilizations? This puzzle is known as the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "If aliens exist, where is everybody?" There are many possible answers. Maybe intelligent life is extremely rare. Maybe civilizations tend to destroy themselves before they can spread across the galaxy. Maybe they exist, but are deliberately hiding. Maybe they have visited, but we did not recognize them. Maybe interstellar travel is simply too difficult, even for advanced civilizations. Maybe we are the first intelligent species to arise in our galaxy. We do not know which answer is correct. The Fermi paradox remains one of the great unsolved mysteries, touching on biology, physics, sociology, and our place in the cosmos. Let us return now to the physical universe and talk about some more extreme objects and phenomena. Let us talk about the hottest and coldest places in the cosmos. The hottest place in the universe that we know of is probably the instant of the Big Bang itself. In the first fraction of a second, temperatures reached trillions of degrees, so hot that matter as we know it could not exist. Only a soup of fundamental particles and energy filled the newborn cosmos. Today, the hottest sustained temperatures occur in the cores of massive stars and in the immediate aftermath of cosmic explosions. The cores of the largest stars reach temperatures of billions of degrees. When neutron stars form, the temperature briefly spikes even higher before cooling down over millions of years. Artificial temperatures have actually exceeded these natural records, at least briefly. The Large Hadron Collider has created conditions hotter than anything in nature today by smashing particles together at nearly the speed of light. For a fleeting instant, temperatures reach trillions of degrees, recreating conditions that have not existed naturally since the Big Bang. On the other end of the scale, the coldest known place in the universe is surprisingly close to home. It is the Boomerang Nebula, a cloud of gas and dust about 5,000 light-years away. The Boomerang Nebula is being rapidly expelled by a dying star at its center. As the gas expands, it cools. The same principle that makes the contents of an aerosol can feel cold when you spray it. The nebula has cooled to about 1 degree above absolute zero, making it colder than the cosmic microwave background radiation that fills all of space. This is remarkable. Everywhere else in the universe, even in the vast voids between galaxies, the CMB provides a minimum temperature of about 2.7 degrees above absolute zero. The Boomerang Nebula has somehow gotten colder than this ambient temperature of space. Absolute zero, minus 273.15 degrees Celsius, is the theoretical minimum temperature. At this temperature, all thermal motion stops. Nothing can get colder. We have never reached absolute zero in any laboratory because quantum mechanics prevents it. There is always some residual energy that cannot be removed. But we have gotten very close, cooling atoms to billionths of a degree above absolute zero. At these ultra-cold temperatures, matter behaves in strange ways. Gases can become superfluids, flowing without any friction. Electrons can pair up in ways that allow electricity to flow without resistance, creating superconductors. These exotic states of matter are being studied intensively, both for fundamental physics and for practical applications like quantum computers. Now, let us discuss some of the most massive objects in the universe and how they challenge our understanding. We have talked about supermassive black holes at the centers of galaxies. But just how massive can these monsters get? The most massive black holes we have found have masses of tens of billions of times that of our Sun. The black hole at the center of the galaxy M87, made famous by the first direct image of a black hole in 2019, has a mass of about 6.5 billion suns. The black hole at the center of the galaxy Holm 15A is estimated at about 40 billion solar masses. How did these behemoths form? Growing a black hole to billions of solar masses takes time. It has to swallow enormous amounts of matter. But we have found quasars, powered by supermassive black holes, from when the universe was less than 1 billion years old. How did black holes grow so large so quickly? This is called the black hole mass problem, and it is one of the puzzles of modern cosmology. One possibility is that these black holes started out much larger than normal. Instead of forming from the deaths of individual stars, they might have formed from the direct collapse of huge clouds of gas in the early universe, creating seed black holes already thousands of times more massive than the Sun. Another possibility is that black holes in the early universe grew much faster than we thought possible. There is a theoretical maximum rate at which a black hole can feed, called the Eddington limit. Above this rate, the radiation from the accreting material would blow away the infalling gas. But maybe black holes can exceed this limit under certain conditions, allowing them to grow faster than expected. We are still working out the details of how the most massive black holes formed. Each new observation of a distant quasar pushes back the timeline and makes the puzzle more challenging. The universe seems to have been very efficient at creating these cosmic monsters. Speaking of massive objects, let us talk about the largest structures in the observable universe: the galaxy superclusters and the cosmic web. Galaxies do not float randomly through space. They are organized into a hierarchy of structures. Individual galaxies like our Milky Way are often part of small groups. These groups are part of larger clusters containing hundreds or thousands of galaxies. And clusters are arranged into superclusters, vast assemblages that can stretch for hundreds of millions of light years. The superclusters themselves are arranged in a pattern called the cosmic web. This is a network of filaments and walls made of galaxies and dark matter, surrounding enormous voids where almost nothing exists. If you could zoom out far enough to see the entire observable universe at once, it would look something like a three-dimensional spider web with bright strands of matter surrounding dark, empty bubbles. The largest known structures in this web are almost incomprehensibly vast. The Hercules Corona Borealis Great Wall is a string of galaxy clusters stretching for about 10 billion light years. That is about 1/9 the diameter of the entire observable universe. It contains billions of galaxies, countless trillions of stars, and enough matter to challenge our understanding of how structures form. The existence of structures this large is actually a problem for cosmology. According to our models, there should not have been enough time since the Big Bang for gravity to assemble matter into structures this size. The Hercules Corona Borealis Great Wall and similar features might indicate that our understanding of cosmic evolution is incomplete. Let us delve deeper into the mysteries of cosmic structure by examining some specific unusual formations that have puzzled astronomers. There is a feature called the giant arc, discovered in 2021. It is a crescent-shaped arrangement of galaxies spanning about 3.3 billion light-years of space. To put that in perspective, our entire Milky Way galaxy is about 100,000 light-years across. The giant arc is more than 30,000 times larger. Structures of this size challenge what is called the cosmological principle, the idea that on very large scales, the universe should look roughly the same in every direction. If we keep finding enormous structures that span significant portions of the observable universe, it might mean the cosmos is less uniform than we thought. Then there is the cold spot we mentioned earlier when discussing the cosmic microwave background. The supervoid associated with this spot is one of the largest individual structures ever identified. A region spanning over 1 billion light years that contains far fewer galaxies than expected. How did such an enormous empty region form? In the standard model of cosmology, voids grow as matter gets pulled away into surrounding filaments and clusters. But creating a void this large might require conditions that are not fully accounted for in our models. These gigantic structures remind us that the universe operates on scales that boggle the human mind. We evolved to understand distances of a few miles, timescales of a few decades. The cosmos operates on distances of billions of light years and timescales of billions of years. Every time we think we have grasped the scale of things, we discover something that humbles us further. Let us turn our attention back to individual objects and discuss some more strange stellar phenomena that have been discovered in recent years. There is a class of stars called Thorne-Zitkov objects, named after the physicists who first proposed them. A Thorne-Zitkov object would be a red giant star with a neutron star at its core. Imagine a normal star with a dead stellar corpse buried at its center. How would such a strange hybrid form? The most likely scenario involves binary star systems. If a red giant expands enough to swallow its neutron star companion, the neutron star might spiral inward and settle at the center instead of simply merging. The result would be a star that looks like a red giant on the outside, but is fundamentally different on the inside. Thorne-Zitkov objects should have unusual chemical signatures because nuclear reactions near the neutron star core would produce elements in unusual abundances. In 2014, astronomers announced they might have found a candidate Thorne-Zitkov object based on its chemical composition, but the identification remains uncertain. These objects, if they exist, are probably extremely rare. Another strange stellar phenomenon involves stars that seem to be older than the universe. How can that be? In the early 2000s, astronomers measured the age of a star called HD 140283 by studying its composition and luminosity. The result came out to about 14.5 billion years, but the universe itself is only about 13.8 billion years old. The star seemed to be older than everything. This was clearly impossible. Either the star's age was wrong, or the age of the universe was wrong. Subsequent measurements refined the age of HD 140283 to about 14 billion years, with an uncertainty that brings it into agreement with the age of the universe. The star is probably one of the oldest known stars, formed when the universe was just a few 100 million years old. But the episode illustrates how measurement uncertainties can create apparent paradoxes. When you are dealing with ages of billions of years, even a small percentage error can be significant. The universe constantly challenges us to refine our measurements and improve our understanding. Let us discuss another category of cosmic oddity: the objects that seem to defy our understanding of stellar physics. There are stars called hypergiants that push against the theoretical limits of how massive a star can be. The most massive stars we have found, like R13601 in the Large Magellanic Cloud, have masses of around 200 times that of our Sun. This is near the theoretical upper limit for stellar mass, called the Eddington limit. Above this limit, the radiation pressure from the star's core should blow away any additional material before it can accumulate. Yet we have hints that even more massive stars might have existed in the early universe. The first generation of stars, sometimes called population Thur stars, formed from pristine hydrogen and helium without any heavier elements. Without these heavier elements to help cool the gas, the protostellar clouds might have grown much larger before collapsing, potentially creating stars hundreds or even thousands of times more massive than the Sun. No population 3 stars have been directly observed because they all died long ago, but their legacy lives on in the heavy elements they created and scattered through space. Every atom of carbon, oxygen, iron, and other elements in your body was forged in the cores of massive stars and spread through the cosmos by supernova explosions. We are quite literally made of stardust, the ashes of ancient stellar giants. On the other extreme, there are objects called brown dwarfs that exist on the border between stars and planets. A brown dwarf is a ball of gas that is too small to sustain hydrogen fusion, the nuclear reaction that powers normal stars. Brown dwarfs are larger than planets, but smaller than the least massive stars, occupying an awkward middle ground. Brown dwarfs glow faintly from the heat left over from their formation and from the gravitational energy released as they slowly contract. But without fusion, they gradually cool and fade over billions of years. Old brown dwarfs might be nearly invisible, dark objects drifting through space. Astronomers have discovered thousands of brown dwarfs, and some of them are truly strange. The coolest brown dwarfs have temperatures similar to a hot oven on Earth. Their atmospheres contain clouds of minerals like enstatite and iron, and possibly even clouds of water. If you could somehow visit one, you would find a world utterly unlike anything in our solar system. Some brown dwarfs have been found wandering alone through space, similar to rogue planets. The distinction between a very large rogue planet and a very small brown dwarf is blurry. Both are isolated objects that formed independently. Both are too small for hydrogen fusion, and both are slowly cooling over cosmic time. The main difference is how they formed. Planets coalesce from disks around stars, while brown dwarfs collapse from gas clouds. Now let us discuss some of the strangest atmospheres and weather patterns found on other worlds. We have already mentioned planets that rain glass and iron, but let us go into more detail about just how extreme exoplanet weather can be. On the gas giant Kepler 7b, astronomers detected patterns that suggest it has clouds on one side but not the other. The clouds appear to be made of silicate particles, essentially sand or glass, carried by winds from the hot daytime side to the cooler evening side where they condense. The hot Jupiter named WASP 43b has been mapped in enough detail to show its atmospheric circulation. The hottest point on the planet is shifted downwind from directly facing the star, carried by powerful jet streams. Winds on this world blow at thousands of kilometers per hour, far faster than any hurricane on Earth. Perhaps the most extreme weather occurs on the exoplanet called Kelt 9b, the hottest known exoplanet. With a daytime temperature of over 4,000 degrees Celsius, this world is hotter than many stars. Its atmosphere contains vaporized metals including iron, magnesium, and sodium. The hydrogen molecules in its atmosphere are being torn apart by the intense heat. This planet is being slowly destroyed by its host star, losing mass as its atmosphere boils away into space. On the other end of the temperature scale, icy moons in our own solar system have their own strange weather. On Saturn's moon Titan, it rains liquid methane. Lakes and seas of hydrocarbons dot the surface. The cycle of evaporation, cloud formation, and precipitation is similar to Earth's water cycle, just with a different chemical playing the role of water. On Neptune's moon Triton, geysers of nitrogen gas erupt from beneath the frozen surface, carrying dark material high into the thin atmosphere. Triton has one of the coldest surfaces in the solar system at minus 235 degrees Celsius. Yet even in this frozen wasteland, there is geological activity driven by subtle internal heating. These alien weather systems remind us that Earth's climate is just one possibility among many. The basic physics of atmospheres, heating, cooling, circulation, condensation, plays out differently depending on the chemistry and conditions involved. Every world is a natural experiment in atmospheric science. Let us now explore another frontier of strangeness, the unexpected connections between things that seem unrelated. One of the strangest discoveries in physics is the principle of quantum entanglement. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, seems to violate our intuitions about how information can travel. Entanglement is real and has been demonstrated countless times in laboratories. It is being developed for technologies like quantum computing and quantum encryption. But what does it mean for our understanding of reality? Some physicists think entanglement reveals that space itself is not fundamental. Instead, space might emerge from a deeper layer of reality, where entanglement is the primary relationship. This idea, called the ER equals EPR conjecture, proposes that entangled particles are connected by tiny wormholes, tunnels through space-time. If true, the fabric of space might be woven from quantum entanglement. Another strange connection is between black holes and thermodynamics. In the 1970s, physicists discovered that black holes behave exactly like thermodynamic systems. They have temperature, entropy, and energy. They obey the laws of thermodynamics. The event horizon area plays the role of entropy, always increasing when black holes merge. This connection between gravity and thermodynamics is still not fully understood. Some theorists think it hints at a deeper unity between quantum mechanics and gravity. Maybe gravity itself emerges from thermodynamics. Maybe space-time is a kind of fluid, with temperature and entropy built in at a fundamental level. The holographic principle is another strange idea that has emerged from theoretical physics. It suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. In a sense, we might be living in a cosmic hologram, where three-dimensional reality is projected from a two-dimensional surface. This sounds like science fiction, but there is serious theoretical support for it. The mathematics of string theory and quantum gravity seems to require something like the holographic principle, and it resolves certain puzzles about black holes and information. The idea that reality might have fewer dimensions than it appears is one of the stranger notions in modern physics. Let us pull back from abstract physics and return to the tangible universe. Let us talk about some of the most beautiful and awe-inspiring objects we have observed. Nebulae are clouds of gas and dust where stars are born and where they die. They come in dazzling varieties, painted by the light of the stars within and around them. The pillars of creation in the Eagle Nebula are among the most famous astronomical images ever taken. These towering columns of gas, several light years tall, are being sculpted by the radiation from nearby young stars. Inside the pillars, new stars are forming even as the columns are being eroded away. The Crab Nebula is the remnant of a supernova explosion witnessed by Chinese astronomers in the year 1054. At its center lies a pulsar spinning 30 times per second, powering the nebula with streams of energetic particles. The nebula glows across the entire electromagnetic spectrum, from radio waves to gamma rays. The Helix Nebula is a planetary nebula, the glowing shell of gas expelled by a dying sun-like star. From Earth, it looks like a giant eye staring across space. At its center is a white dwarf, the exposed core of the original star, slowly cooling over billions of years. The Helix Nebula shows us what our own sun will look like in about 5 billion years. These objects are more than just beautiful. They are laboratories for studying the life cycles of stars. They show us the raw materials from which new worlds will form. They remind us that creation and destruction are linked in the cosmic dance of matter and energy. Let us talk about the search for habitable worlds beyond Earth. The discovery of thousands of exoplanets has revolutionized our understanding of what is possible. Many of these planets orbit in the habitable zones of their stars, where temperatures might allow liquid water to exist. Proxima Centauri b is the closest known exoplanet that might be habitable. It orbits the red dwarf star nearest to our Sun, just 4.2 light-years away. The planet is slightly larger than Earth and receives about the right amount of energy from its star for liquid water to exist. But there are concerns. Red dwarfs can produce powerful flares that might strip away atmospheres and sterilize surfaces. The TRAPPIST-1 system contains 7 Earth-sized planets, at least 3 of which orbit in the habitable zone. This system has captured the imagination of many because it offers multiple chances for habitable conditions in a single solar system. The planets are close enough together that from the surface of one, you could see others as clearly as we see our moon. Kepler 452b was nicknamed Earth's bigger, older cousin when it was discovered. It orbits a sun-like star at almost exactly the same distance that Earth orbits our sun. The planet is larger than Earth, but otherwise it is one of the best candidates for an Earth-like world we have found. But we should be careful about assuming habitability. A planet in the habitable zone is not automatically habitable. It needs the right atmosphere, the right surface conditions, protection from radiation, and probably other factors we do not fully understand. Mars is in our Sun's habitable zone, but is a frozen desert with a thin atmosphere. Venus is just barely outside the habitable zone, but is a hellish furnace with crushing atmospheric pressure. The question of what makes a world truly habitable remains open. Every new exoplanet discovery gives us more data to work with. Eventually, we hope to analyze the atmospheres of Earth-like planets for signs of life, oxygen, methane, other molecules that might indicate biological activity. The search for life beyond Earth is one of the most profound scientific quests in human history. Let us now contemplate the ultimate fate of the universe. What will happen to all these strange and wonderful objects in the far future? If dark energy continues to accelerate the expansion of the universe, the future looks cold and empty. Galaxies will drift apart until they are beyond each other's cosmic horizons. The stars will burn out over trillions of years. Black holes will slowly evaporate through Hawking radiation over timescales that dwarf the current age of the universe. Eventually, even atoms might decay. If protons are not truly stable, which some theories suggest, then matter itself will slowly dissolve over time periods so long they require new mathematical notation to express. The universe would become a thin soup of particles and radiation, spreading ever more thinly through ever more space. This fate, sometimes called the heat death of the universe, sounds bleak, but it is unimaginably far in the future. The current age of the universe is about 14 billion years. The last stars will not burn out for trillions of years. The last black holes will not evaporate for googol years, a 1 followed by 100 zeros. We have plenty of cosmic time ahead. Some physicists speculate about other possibilities. Could intelligent life somehow survive indefinitely by harvesting energy more and more efficiently? Could new universes be created artificially, allowing consciousness to escape a dying cosmos? Could the expansion of the universe reverse, leading to a big crunch that might spark a new Big Bang? We do not know. The ultimate fate of the universe remains uncertain, dependent on physics we have not yet discovered. But contemplating these vast timescales puts our current existence in perspective. We live in a young, vibrant universe, full of stars and galaxies and the potential for discovery. The strangeness we have catalogued in this exploration is just the beginning. Let us return to the present and summarize the incredible journey we have taken through the strangest discoveries in space. We began with the invisible universe, dark matter that holds galaxies together, and dark energy that pushes them apart. Together, these mysterious substances make up 95% of everything that exists, yet we do not know what they are. We explored extreme stellar objects, neutron stars that pack the mass of the sun into a city-sized ball, pulsars that spin hundreds of times per second, and magnetars with magnetic fields strong enough to scramble atoms from halfway across the solar system. We encountered hypervelocity stars ejected from their galaxies, mysterious dimming events around distant suns, and quasars that outshine entire galaxies from billions of light years away. We pondered rogue black holes wandering through the void, the great attractor pulling galaxies across hundreds of millions of light years, and cosmic voids larger than anything we can easily imagine. We discovered strange new worlds, planets made of diamond, planets that rain glass and iron, and rogue planets drifting in eternal darkness with no star to call home. We listened to the oldest light in the universe, the cosmic microwave background, and puzzled over its mysterious cold spot. We detected fast radio bursts and gamma-ray bursts, cosmic signals that flash and fade before we can fully understand them. We explored the nature of time itself near black holes, where seconds can stretch into centuries. We learned about exotic matter that might exist in the cores of neutron stars, strange quarks that might be more stable than ordinary matter, and theoretical objects that push our physics to its breaking point. We touched on the fastest things in the universe, particles accelerated to nearly the speed of light, and the expansion of space that carries galaxies beyond our cosmic horizon. We considered the search for extraterrestrial intelligence, the puzzling silence of the cosmos, and signals like the wow, signal that tantalize us with the possibility that we might not be alone. We examined the hottest and coldest places known to exist, from the trillion-degree instance after the Big Bang to the -270-degree chill of the Boomerang Nebula. And we contemplated the ultimate fate of everything, the slow heat death that awaits a universe dominated by dark energy, stretching across timescales so vast they challenge comprehension. Throughout this exploration, one theme has emerged over and over. The universe is stranger than we expected. Every time we develop a new way to observe the cosmos, we find things that surprise us. Every theory that seemed complete has been challenged by new discoveries. Every limit we thought was fixed has been pushed or broken. This is the essence of science. We build models of reality, test them against observations, and revise them when they fall short. The strangeness of the universe is not a bug, but a feature. It drives us forward, motivates new investigations, and reminds us that there is always more to learn. Think about how much has changed in just a century. 100 years ago, we did not know the universe was expanding. We did not know other galaxies existed. We did not know about neutron stars, black holes, dark matter, dark energy, exoplanets, quasars, pulsars, or most of the other phenomena we have discussed. What will we know 100 years from now? What strange new discoveries await future generations of scientists? The history of astronomy suggests the answer will be more than we can imagine. Perhaps we will finally understand what dark matter and dark energy really are. Perhaps we will detect gravitational waves from the earliest moments of the Big Bang. Perhaps we will find definitive evidence of life beyond Earth, or confirm that we are alone. Perhaps we will discover new physics that makes our current theories look as incomplete as Newton's physics looked after Einstein. One thing seems certain: the universe will continue to surprise us. It always has. Now let us go even deeper into some of the phenomena we have touched on, exploring the details that make each one so remarkable. Consider the life cycle of a massive star in more detail. A star like our Sun will eventually exhaust its hydrogen fuel, expand into a red giant, shed its outer layers, and leave behind a white dwarf. That process takes about 10 billion years and ends relatively peacefully. But for stars more than 8 times the mass of our Sun, the ending is far more dramatic. These massive stars burn through their fuel much faster, living only a few million years instead of billions. They fuse heavier and heavier elements in their cores: helium, carbon, oxygen, neon, silicon, creating an onion-like structure with different elements in different layers. But when the core reaches iron, fusion stops producing energy. Iron is the end of the line for stellar nucleosynthesis. Fusing iron actually absorbs energy instead of releasing it. Without the outward pressure of fusion to balance gravity, the core collapses. This collapse happens in a fraction of a second. The core, roughly the mass of the Sun, crunches down to the size of a city. The outer layers of the star, suddenly lacking support, fall inward and then rebound off the incredibly dense core. A shock wave blasts outward through the star. The result is a supernova, one of the most energetic events in the universe. For a few weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of normal stars. The shock wave creates elements heavier than iron, gold, uranium, platinum, and scatters them across space. What remains depends on the original mass of the star. For most massive stars, the core becomes a neutron star. For the very most massive, even neutron degeneracy pressure cannot halt the collapse, and the core continues falling until it forms a black hole. Supernovae are cosmic recycling centers. They take hydrogen and helium, the simple elements created in the Big Bang, and return complex elements to the interstellar medium. Future generations of stars and planets form from gas enriched by these explosions. Without supernova, there would be no rocky planets, no carbon, no life as we know it. The Crab Nebula, which we mentioned earlier, is the remnant of a supernova that was bright enough to be visible in daylight when it exploded in the year 1054. Chinese astronomers recorded it as a guest star that remained visible for nearly 2 years. Today, almost 1,000 years later, the nebula continues to glow, powered by the pulsar at its center. Every few decades, a supernova occurs in a galaxy like the Milky Way. The last one visible to the naked eye from Earth was in 1604, before telescopes were invented. Astronomers eagerly await the next nearby supernova, which would provide an unprecedented opportunity to study these explosions up close with modern instruments. The star Betelgeuse, the red supergiant in the shoulder of Orion, is one candidate for a relatively nearby supernova. This star has already exhausted the hydrogen in its core and is fusing heavier elements. It will explode within the next 100,000 years, possibly much sooner. When it does, it will be visible in daylight for weeks, a beacon reminding us of the violent processes that shape the cosmos. Let us explore another aspect of cosmic violence: the collisions between galaxies. Galaxies are not static. They move through space, drawn by gravity toward their neighbors. When two galaxies meet, the results can be spectacular. The Andromeda Galaxy, our nearest large galactic neighbor, is heading toward the Milky Way at about 400,000 kilometers per hour. In about 4.5 billion years, the two galaxies will collide. But collision is a misleading word. Galaxies are mostly empty space. When they merge, individual stars almost never hit each other. Instead, the gravitational interactions distort both galaxies, pulling out long tails and streams of stars. We can see galaxy collisions in progress throughout the universe. The Antennae galaxies are a famous example. Two spiral galaxies in the process of merging, with long tails of stars streaming away from the interaction. The Mice galaxies show a similar process at an earlier stage, their shapes already distorted, but their cores not yet merged. Galaxy mergers trigger bursts of star formation. The gravitational interactions compress gas clouds, causing them to collapse and form new stars. Some of the most intensely star-forming galaxies we have observed are colliding systems, where the interaction has sparked a frenzy of stellar birth. At the center of merging galaxies, the supermassive black holes eventually spiral together and merge as well. This process releases tremendous amounts of gravitational wave energy. Future space-based gravitational wave detectors should be able to detect these mergers from across the universe, opening a new window on cosmic evolution. When the Milky Way and Andromeda merge, the result will be a new, larger galaxy, sometimes nicknamed Milkdromeda or Milkomeda. Our solar system will probably survive the merger, although it might be flung to a different location within the combined galaxy. The night sky would be transformed with a new galactic structure overhead. But the sun will still be shining, and any distant descendants of humanity would witness one of the most dramatic events in the life of our cosmic neighborhood. Let us turn to a topic we have mentioned, but not fully explored: gravitational waves. In 1915, Albert Einstein published his general theory of relativity, which describes gravity not as a force, but as the curvature of space-time. Massive objects bend the fabric of space and time around them, and other objects move along the curved paths created by this bending. Einstein realized that accelerating masses should create ripples in space-time that propagate outward at the speed of light. These gravitational waves would stretch and squeeze space itself as they pass through, alternately making distances slightly longer and shorter. But the effect is incredibly tiny. Even the most violent cosmic events would produce gravitational waves that stretch space by less than the width of a proton. For a century after Einstein's prediction, gravitational waves remained theoretical because no instrument was sensitive enough to detect them. That changed in 2015, when the LIGO observatories made the first direct detection of gravitational waves. The signal came from two black holes, each about 30 times the mass of the Sun, spiraling together and merging about 1.3 billion light-years away. The entire event lasted less than a second, but it produced a distinctive chirp as the black holes orbited faster and faster before merging. Since that first detection, dozens more gravitational wave events have been observed. We have detected black hole mergers of various sizes, neutron star mergers that also produced light signals, and possible black hole neutron star mergers. Each detection teaches us something new about these extreme events and the populations of compact objects in the universe. Gravitational wave astronomy is still in its infancy. Current detectors are sensitive to mergers involving stellar mass objects. Future detectors, including space-based observatories like LISA, will be sensitive to much lower frequencies, allowing us to detect mergers of supermassive black holes and possibly even echoes from the Earth's very early universe. Gravitational waves carry information that light cannot provide. They let us probe the interiors of neutron stars, test general relativity in extreme conditions, and observe events that produce little or no electromagnetic radiation. They are a completely new way of listening to the cosmos. Let us explore the bizarre physics of neutron stars in more detail. We have mentioned that neutron stars are incredibly dense, a teaspoon of neutron star material weighing billions of tons. But the internal structure of these objects is even stranger than their density suggests. The outer crust of a neutron star is probably similar to ordinary dense matter, with atomic nuclei arranged in a crystalline lattice. But as you go deeper, the pressure increases and the matter changes. The nuclei become larger and more deformed, eventually merging into structures sometimes called nuclear pasta, because they resemble spaghetti and lasagna at the atomic scale. Below the crust is the outer core, where matter consists primarily of neutrons with some protons and electrons. This is the neutron matter that gives neutron stars their name. But even this description is simplified. In the inner core, at the highest densities, we do not really know what happens. The matter might transition to quark matter, where individual quarks roam freely rather than being confined in protons and neutrons. Or there might be even more exotic forms of matter that we have not imagined. Neutron stars also have incredible magnetic fields. While Earth's magnetic field is about half a Gauss, a typical neutron star's field is 1 trillion Gauss. Magnetars, as we discussed, can reach field strengths of 1 quadrillion Gauss or more. These magnetic fields affect the behavior of matter in unusual ways. In strong magnetic fields, atoms become elongated along the field lines. The energy levels of electrons are quantized differently. Light travels at different speeds, depending on its polarization. Physics works differently around neutron stars than anywhere else in the universe we can observe. Pulsars, the rapidly spinning neutron stars that emit beams of radiation, are also incredibly precise timekeepers. The most stable millisecond pulsars lose only about 1 second every few 100 million years. This makes them useful for a variety of scientific purposes. Arrays of pulsars spread across the galaxy can be used to detect very low-frequency gravitational waves. These waves, from supermassive black hole binaries, cause tiny changes in when pulsar signals arrive at Earth. By monitoring many pulsars simultaneously, astronomers can search for the correlations that would indicate a passing gravitational wave. This technique has recently yielded results. In 2023, several pulsar timing array collaborations announced evidence for a gravitational wave background, a continuous hum of gravitational waves from many sources throughout the universe. This may be the first detection of gravitational waves from supermassive black hole binaries. Now let us discuss a phenomenon we have not yet covered: gravitational lensing. When light passes near a massive object, it bends. This effect, predicted by general relativity, means that massive objects can act as lenses, magnifying and distorting the images of more distant objects behind them. The first confirmation of gravitational lensing came in 1919, when an eclipse expedition measured the positions of stars near the Sun and found they were slightly shifted from their expected positions. The Sun's mass was bending their light. Today, gravitational lensing is a powerful tool for astronomy. Galaxy clusters, containing enormous amounts of matter, can lens background galaxies so strongly that they appear as distorted arcs and multiple images. By analyzing these lensing effects, astronomers can map the distribution of matter in the cluster, including the dark matter that cannot be seen directly. Strong lensing, where the distortion is dramatic, creates beautiful cosmic mirages. A distant galaxy might appear as a complete ring surrounding the foreground lens, an effect called an Einstein ring. Or it might be split into multiple images, arriving at Earth from slightly different directions after taking different paths around the lens. Weak lensing, where the distortion is subtle, is even more powerful for studying dark matter. By measuring the slight ellipticities of millions of background galaxies, astronomers can reconstruct the matter distribution across vast regions of the universe. These surveys have confirmed the existence of dark matter and helped constrain its properties. Microlensing, where an individual star acts as a lens, can detect objects that produce no light of their own. When a dark object passes between Earth and a distant star, the lensing effect causes the star to briefly brighten. This technique has been used to search for black holes, brown dwarfs, and even rogue planets drifting through the galaxy. Gravitational lensing also allows us to see farther into the universe than would otherwise be possible. The most distant galaxies we have observed were magnified by foreground clusters acting as cosmic telescopes. Without lensing, these faint distant galaxies would be invisible even to our most powerful instruments. Let us now explore the concept of cosmic inflation, a period of extremely rapid expansion in the very early universe. According to the standard Big Bang model, the universe began in a hot, dense state and has been expanding ever since. But the standard model has some puzzles. Why is the universe so uniform on large scales? Why is the geometry of space so flat? How did matter get distributed in the particular pattern that led to today's cosmic structure? In the early 1980s, physicists proposed that a brief period of inflation could solve these puzzles. During inflation, the universe expanded exponentially, growing by a factor of at least 10 to the 26th power in a tiny fraction of a second. This expansion smoothed out any irregularities, flattened the geometry, and stretched microscopic quantum fluctuations to cosmic scales. These stretched quantum fluctuations became the seeds of cosmic structure. Regions that were slightly denser attracted more matter through gravity over billions of years, eventually forming the galaxies and clusters we see today. The pattern of fluctuations in the cosmic microwave background matches what inflation predicts remarkably well. Inflation also makes a prediction that has not yet been verified. The rapid expansion should have created gravitational waves that left a subtle imprint on the polarization of the cosmic microwave background. Detecting this imprint, called B-mode polarization, would be strong evidence for inflation. Several experiments are searching for this signal, but it has proven difficult to separate from contamination by dust in our own galaxy. A confirmed detection would be a triumph for cosmology, connecting quantum mechanics, general relativity, and the structure of the entire universe. But what caused inflation? What drove this brief period of exponential expansion? The standard proposal is a hypothetical field called the inflaton, which briefly dominated the energy of the universe before decaying into ordinary matter and radiation. But we have no direct evidence for the inflaton, and alternative models of inflation continue to be developed. Some versions of inflation predict that our observable universe is just one bubble in a vast multiverse. Inflation might be eternal, constantly producing new bubble universes with potentially different physical laws. If this is true, the ultimate explanation for why our universe has the properties it does might be that we could only exist in a universe with these particular properties. These ideas push against the boundary between science and philosophy. Can we ever test the existence of other universes? Is a multiverse a scientific theory or metaphysical speculation? Different scientists have different answers, and the debate continues. Let us bring our exploration toward a close by, reflecting on what all these strange discoveries mean for our understanding of existence. The universe is not the simple, predictable place our ancestors imagined. It is full of objects and phenomena that challenge our intuitions at every turn. Matter that we cannot see holds galaxies together. Energy that we do not understand is pushing the universe apart. Stars spin hundreds of times per second and emit radiation stronger than anything we can create. Planets drift alone through the darkness between stars. Space itself ripples when massive objects collide. Yet for all its strangeness, the universe is comprehensible. We can observe these phenomena, measure them, build mathematical models to describe them. The laws of physics that govern atoms in a laboratory also govern neutron stars and black holes. The same gravity that makes apples fall shapes the evolution of galaxies. This combination of strangeness and comprehensibility is remarkable. There is no logical reason why the universe should be understandable. It could have been chaotic, arbitrary, beyond analysis. Instead, it reveals patterns and regularities that human minds can grasp. We are creatures of this strange universe, made from atoms forged in stellar cores, walking around on a planet orbiting an ordinary star in an average galaxy. Our brains evolved to navigate African savannas, to find food and avoid predators. Yet these same brains can understand black holes and dark energy and the cosmic microwave background. Perhaps the strangest thing about the universe is that it created beings capable of wondering about its strangeness. As we look up at the night sky, we are looking at the past. The light from stars left those stars years, centuries, or millennia ago. The light from galaxies has been traveling for millions or billions of years. When we observe the cosmic microwave background, we are seeing the universe as it was almost 14 billion years ago. Astronomy is a form of time travel. By looking far away, we look back in time. We can watch the universe evolve, from the smooth young cosmos of the CMB to the rich structure of today. We can see galaxies forming, stars being born and dying, the cosmic web assembling itself over billions of years. And as we watch, we realize that we are watching our own origin story. Every atom in your body was once part of a star. Some were forged in the Big Bang, cooked in stellar cores, scattered by supernovae, incorporated into planets, and eventually organized into the complex structures we call life. You are the universe experiencing itself. When you wonder at the strangeness of black holes and magnetars and diamond planets, the universe is wondering at itself. This is perhaps the most profound thing we can say about the strange discoveries in space. They are not just curiosities or facts to memorize. They are part of the story of how we came to be. They connect us to the largest scales and oldest times. They remind us that existence is not ordinary, not mundane, but extraordinary and precious. The night sky is full of wonders waiting to be discovered. Every generation of astronomers has found things their predecessors could not have imagined. Future generations will find things we cannot imagine today. The universe will continue to surprise us, challenge us, and inspire us. And somewhere out there, perhaps, other beings are looking at their own night skies and wondering at their own strange discoveries. Perhaps one day we will compare notes. Perhaps we will find that the universe is stranger than any of us knew. Perhaps we will discover that the greatest wonders are still ahead. Until then, we keep looking. We keep asking questions. We keep building better telescopes and developing new theories. We keep pushing against the boundaries of what we know, because the strangeness of the universe demands nothing less. The stars are calling. What strange thing will you discover next? Observations favor the constant dark energy scenario, but the uncertainties are large enough that other possibilities cannot be ruled out. The ultimate fate of the cosmos depends on physics we do not yet fully understand. Let us explore the mysteries of black hole interiors. One more time. We talked about singularities and information paradoxes, but there is more strangeness to consider. For a rotating black hole, which is the more realistic scenario, since all astrophysical black holes should spin, the mathematics of general relativity predicts even stranger structures. Instead of a single point singularity, there is a ring singularity, and beyond the ring, the equations suggest there might be tunnels leading to other regions of space-time. These tunnels, sometimes called wormholes, could in principle connect distant parts of the universe, or even different universes entirely. Some physicists have speculated that the singularities we call the beginning and end of black holes might actually be passages to somewhere else. But there are serious problems with the idea of traversable wormholes. The mathematical solutions that allow them are probably not physically realistic. Any attempt to travel through would likely be fatal, and maintaining a wormhole would require exotic matter with negative energy density, something that may not exist. Still, the fact that these structures appear in our equations at all is remarkable. General relativity keeps producing surprises, possibilities that stretch our imagination, even if they turn out not to be realized in nature. Let us also consider the horizon problem, one of the puzzles that inflation was designed to solve. When we look at the cosmic microwave background, it appears remarkably uniform. Regions on opposite sides of the sky have almost exactly the same temperature. But here is the puzzle. Those regions are so far apart that light has never had time to travel between them. In the standard Big Bang model without inflation, there was no way for those regions to exchange information, to come into thermal equilibrium. How did they end up at the same temperature if they could never interact? Inflation solves this by proposing that before inflation, these regions were close enough to be in causal contact. They reached equilibrium when they could still interact. Then inflation stretched them apart so fast that light could not keep up. The uniformity was established before inflation and preserved afterward. This is an elegant solution, but it requires accepting that the universe underwent a period of expansion even more extreme than the normal Big Bang. Inflation is widely accepted in cosmology, but some researchers have proposed alternatives that achieve similar results without quite as dramatic an expansion. The strangeness of the universe extends to its very origins. Before the Big Bang, if that phrase even makes sense, what was there? What caused the universe to begin? Could the universe have existed forever in some form? These questions push beyond what science can currently answer. Our physical theories break down at the very beginning, when the universe was incredibly hot, dense, and small. Quantum gravitational effects, which we do not yet understand, must have dominated. What we call the Big Bang might have been a transition from some prior state that our current physics cannot describe. Some theories propose that the universe emerged from a quantum fluctuation in a pre-existing vacuum. Others suggest that the Big Bang was triggered by the collision of higher dimensional objects called brains. Still others imagine an eternal inflation where Big Bangs are constantly occurring, creating new pocket universes in an endless cosmic landscape. We do not know which, if any, of these ideas is correct. The origin of the universe remains one of the deepest mysteries, perhaps permanently beyond our reach. Let us return to the topic of strange star systems and examine some more peculiar configurations. Binary star systems, where two stars orbit each other, are common in the galaxy. But some binary systems are especially weird. In cataclysmic variables, a white dwarf accretes matter from a companion star, leading to periodic outbursts as the accumulated material undergoes thermonuclear burning. In symbiotic stars, a white dwarf is buried in the outer atmosphere of a red giant, creating a complex interacting system. X-ray binaries are among the most energetic binary systems. These contain a neutron star or black hole that is pulling matter from a companion star. As the matter spirals in, it heats up to millions of degrees and emits powerful X-rays. These systems can flare and vary on timescales from milliseconds to months, providing windows into the physics of extreme gravity. Some star systems contain 3 or more stars. The Alpha Centauri system, our nearest stellar neighbor, is actually a triple star system. Alpha Centauri A and B are a binary pair, while Proxima Centauri, the closest star to our Sun, orbits this pair at a much greater distance. In more extreme cases, stars can be arranged in hierarchical systems of 4, 5 or more members. These systems are dynamically challenging to maintain because gravitational interactions can destabilize orbits over time. Yet they exist, testimony to the variety of configurations that can form from collapsing gas clouds. Let us consider one more category of cosmic strangeness: the objects that do not quite fit into our classification schemes. We mentioned brown dwarfs, objects too small to be stars but too large to be planets. There are other objects that blur the boundaries. Super-Jupiters, planets more massive than Jupiter, can overlap in mass with the smallest brown dwarfs. Distinguishing between them requires knowing how they formed, which is often difficult to determine. Then there are sub-brown dwarfs, objects smaller than brown dwarfs but larger than planets, that formed by direct collapse from gas clouds rather than in circumstellar disks. Are these planets or failed stars? The question is not just semantic, but touches on how we define and categorize objects in the universe. Planemos, short for planetary mass objects, is a term proposed for objects of planetary mass regardless of how they formed or where they are. This category would include traditional planets, rogue planets, and any small objects drifting through space. The terminology is still being debated. There are also protoplanets, embryonic planets still in the process of forming. We have detected some of these in young planetary systems, watching as planets are born before our eyes. These observations are challenging to make but incredibly valuable for understanding how solar systems come together. Some objects defy classification entirely. Is the Plutoids really a planet? What about the other dwarf planets in the Kuiper Belt? Where do asteroids end and dwarf planets begin? These questions seem trivial compared to the mysteries of dark energy, but they remind us that even nearby objects can challenge our understanding. Now, let us take a moment to appreciate the technology that has revealed these wonders. Without telescopes, we would know nothing of neutron stars, exoplanets, or dark matter. The history of astronomy is a history of better instruments revealing deeper truths. The first telescopes were simple affairs, tubes with lenses that Galileo pointed at the moon and planets. They revealed craters, moons of Jupiter, and phases of Venus, overturning ancient assumptions about the cosmos. Reflecting telescopes, using mirrors instead of lenses, allowed larger apertures and less distortion. They could gather more light, see fainter objects, and resolve finer details. The great observatories of the 19th and 20th centuries used ever larger mirrors to probe ever deeper into space. Radio astronomy opened a new window in the mid-20th century. Suddenly, we could see quasars, pulsars, and cosmic microwave background. Objects invisible to optical telescopes became prominent in radio wavelengths. The universe looked completely different. X-ray and gamma-ray astronomy required getting above Earth's atmosphere, since these high-energy photons are absorbed before reaching the ground. Satellites and space telescopes open these windows, revealing black holes feeding on gas, neutron stars flaring, and gamma-ray bursts exploding across the cosmos. Infrared astronomy showed us cool objects that emit little visible light, including brown dwarfs, protoplanetary disks, and the warm dust of distant galaxies. Ultraviolet revealed the hottest, youngest stars and the intergalactic medium. Each wavelength told a different story about the same universe. And now, gravitational wave astronomy has opened yet another window. We are no longer limited to electromagnetic radiation. We can feel the ripples in space-time itself, hearing the universe as well as seeing it. Future observatories will continue this trend. The James Webb Space Telescope is already showing us galaxies from the early universe in unprecedented detail. Next-generation ground-based telescopes with mirrors tens of meters across will push the limits of what we can resolve. Space-based gravitational wave detectors will listen to frequencies too low for ground-based instruments. Neutrino observatories might detect signals from the cores of supernovae or the centers of active galaxies. Each new instrument has the potential to reveal something completely unexpected. That is the lesson of history. We build instruments to answer specific questions, and they end up showing us things we never imagined asking about. As we bring this exploration to its final stages, let us reflect on what the strangest discoveries in space tell us about our own existence. We are tiny creatures on a small planet, living for a cosmic instant in a vast universe full of wonders we are only beginning to understand. The distances are so great, the timescales so long, the energy so immense, that they dwarf anything in human experience. Yet we are not insignificant. We are the part of the universe that looks back at itself. We are the part that asks questions, seeks answers, and marvels at what it finds. In all the billions of galaxies, on all the trillions of planets, for all we know, beings like us are rare or unique. The strangeness of the universe is not something to fear. It is something to celebrate. Every black hole, every neutron star, every rogue planet, every fast radio burst is a reminder that reality is far richer than everyday experience suggests. There is always more to learn, always more to discover, always more to wonder at, and that wonder connects us. Humans have looked at the stars for as long as we have been human. We have told stories about them, navigated by them, worshipped them, and studied them. The strange discoveries of modern astronomy are the latest chapter in a story that stretches back to the first campfires and the first questions about what those lights in the sky might be. We are made of stardust, born from the ashes of ancient suns, living on a world circling an ordinary star in a galaxy among billions. The atoms in your body have journeyed across light years and through billions of years to arrive at this moment. You are the universe experiencing itself, wondering at its own strangeness. Take that thought with you as you look at the night sky. The stars are not just distant lights. They are nuclear furnaces forging the elements of future worlds. The darkness between them is not empty. It is full of dark matter, gravitational waves, and secrets waiting to be discovered. The universe is strange. The universe is wonderful, and we are part of it. That is what these discoveries ultimately teach us. Not just facts about distant objects, but something profound about our place in the cosmos. We belong to something vast and ancient and endlessly surprising. We are connected to every star, every galaxy, every mysterious force shaping the universe. And every time we learn something new about the strangeness of space, we learn something new about ourselves. So keep looking up, keep wondering, keep asking questions. The universe has secrets enough to occupy us for eternity, and we have only just begun to uncover them. What will you discover next? Let us take one final journey through some additional cosmic marvels that deserve our attention before we close. Consider the phenomenon of stellar nurseries, the vast clouds of gas and dust where new stars are born. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion, is one of the nearest and best studied. Deep within its swirling clouds, young stars are igniting for the first time, their radiation carving out cavities in the surrounding gas. These stellar nurseries can be truly immense. The Carina Nebula spans over 300 light-years and contains some of the most massive stars known. Eta Carinae, one of the most luminous and unstable stars in our galaxy, lives there, occasionally erupting in outbursts that make it visible across vast distances. The process of star formation is itself strange and wonderful. A cloud of gas, initially spread across light years, begins to contract under its own gravity. As it shrinks, it spins faster, like an ice skater pulling in her arms. A disk forms around the central condensation, and within that disk, planets begin to coalesce. The protostar at the center grows hotter as gravitational energy is converted to heat. Eventually, when the core reaches about 10 million degrees, hydrogen fusion ignites and a new star is born. The whole process takes millions of years, a blink in cosmic terms, but far longer than human history. We have watched this process unfold in time-lapse, comparing images of stellar nurseries taken years or decades apart. We can see jets of gas shooting from young stars, disk shadows silhouetted against background nebulae, and the gradual clearing of material as stars establish themselves. Now, let us consider the strangest orbits in the universe. Most objects follow elliptical paths, as described by Johannes Kepler 4 centuries ago. But some orbits are far more exotic. There are stars that follow hyperbolic paths, moving so fast that they will never return. These include the hypervelocity stars we discussed earlier, ejected from their galaxies entirely. Their orbits are not closed curves, but open paths leading to forever. Some binary stars have orbits so elongated that their closest approach brings them nearly together, while their farthest separation stretches across vast distances. These extreme ellipses can lead to dramatic interactions at closest approach, with mass transfer, tidal distortion, and even stellar mergers. Planets in multiple star systems can have remarkably complex paths. In the Alpha Centauri system, any planets around the binary pair would feel the constantly shifting gravitational influence of two stars. Their orbits would wobble and precess in complicated patterns. We have found exoplanets on orbits tilted at extreme angles to their host stars, orbits that take them from scorching proximity to frigid distance, and orbits that seem unstable over long timescales. The solar system we grew up in, with its neat circular orbits in roughly the same plane, turns out to be unusual. Let us also appreciate the role of magnetic fields throughout the cosmos. We have discussed magnetars with their trillion times stronger fields than refrigerator magnets. But magnetic fields play crucial roles everywhere. The Sun has a magnetic field that drives its 11-year cycle of activity. Sunspots are regions of intense magnetic field. Solar flares and coronal mass ejections occur when magnetic field lines reconnect, releasing stored energy in dramatic bursts. Galaxies have magnetic fields that permeate their interstellar medium. These fields are weak compared to magnetars, but they span tens of thousands of light years. They influence how cosmic rays propagate, how gas collapses to form stars, and how the interstellar medium is structured. Even the vast spaces between galaxy clusters have magnetic fields, though incredibly faint. The origin of these intergalactic fields is a mystery. They might be relics from the very early universe, amplified over cosmic time by turbulent motions. Magnetic fields are everywhere in the cosmos, shaping the behavior of ionized gas, accelerating particles to enormous energies, and creating the conditions for some of the most extreme phenomena we observe. Let us revisit the concept of cosmic time and what it means to observe distant objects. When we look at a galaxy a billion light years away, we see it as it was a billion years ago. But what is that galaxy doing now? The question is more complicated than it seems. According to Einstein's relativity, there is no universal now. Simultaneity depends on the observer's state of motion. What happens now at a distant location is fundamentally ambiguous. We can only talk about events in our past light cone, the set of points in space-time from which light has had time to reach us. This means the universe we observe is not a snapshot of a single moment, but a collection of different times stitched together by the light that reaches us. Nearby objects show us recent times. Distant objects show us ancient times. The cosmic microwave background shows us the universe as it was 400,000 years after the Big Bang. In a sense, we see cosmic history spread out before us. The farther we look, the deeper we look into the past. Astronomy is archaeology with light, excavating layers of time from the photons that arrive at our telescopes. Now let us discuss the role of supercomputers in understanding these strange phenomena. Many of the processes we have described cannot be recreated in laboratories. We cannot build a neutron star or make a galaxy collision happen on demand, but we can simulate these events on powerful computers. Modern astrophysical simulations can track the evolution of millions or billions of particles, following the laws of physics as matter clumps, heats, cools, and radiates. These simulations have become essential tools for testing our theories against observations. Simulations of galaxy formation show how dark matter halos grow and merge, how gas falls into these halos and forms stars, and how black holes at galactic centers influence their surroundings. When simulations match observations, we gain confidence that our understanding is correct. When they differ, we learn where our theories need improvement. Similarly, simulations of neutron star mergers predict the gravitational wave signals we should detect, the elements that should be produced, and the light that should be emitted. Comparing these predictions to actual observations lets us test our models of nuclear matter under extreme conditions. The interplay between observation, theory, and simulation is what advances our understanding. Strange discoveries drive new questions. Theories propose answers. Simulations test whether those answers make sense. And new observations either confirm our ideas or send us back to the drawing board. let us take one more moment to appreciate the human element in all of this. Behind every strange discovery is a person or team of people who work to make it possible. Astronomers spend long nights at telescopes, waiting for clouds to clear and instruments to cooperate. Theorists fill blackboards with equations, searching for patterns that explain observations. Engineers build instruments of incredible precision, pushing technology to its limits. Computer scientists write code that processes billions of data points. Students learn and eventually push beyond what their teachers knew. Science is a human activity, done by humans with all our limitations and strengths. We get tired, make mistakes, have arguments, and occasionally have breakthroughs. The history of astronomy is full of lucky accidents, missed opportunities, bitter rivalries, and moments of pure joy. When we talk about strange discoveries in space, we are really talking about human achievements. The universe did not explain itself. People figured it out, one observation at a time, one theory at a time, building on the work of generations before. And this process continues today. Somewhere right now, someone is analyzing data that might reveal something never seen before. Somewhere, a theorist is having an insight that will change how we think about the cosmos. Somewhere, an engineer is solving a problem that will enable the next great observatory. The strangeness of the universe is matched only by the ingenuity of the humans who study it. As we truly come to the end of our journey now, let us hold on to that sense of connection. You, reading this, are part of the story. Your curiosity continues the ancient human tradition of looking up and wondering. Your questions drive the search for answers. The strangest things we have discovered in space are not just facts about distant objects. They are invitations. Invitations to learn more, to wonder more, to keep asking why the universe is the way it is. Maybe one of those questions will lead to the next great discovery. Maybe the strangest things in space are things we have not even imagined yet, waiting for someone to think the right thoughts and look in the right place. The cosmos is generous with its mysteries. It gives us plenty to wonder about, plenty to study, plenty to discover. All we have to do is keep looking. So as you go about your day, remember that you live in a universe where stars can spin hundreds of times per second, where invisible matter holds galaxies together, where planets drift alone through the darkness, and where the fabric of space itself ripples when massive objects collide. Remember that you are part of this strange and wonderful cosmos. You are made from its materials, shaped by its processes, alive in a tiny corner of its vastness. And remember that the story is not over. Every strange discovery raises new questions. Every answer leads to new mysteries. The universe has been surprising us for as long as we have been paying attention, and there is no reason to think it will stop now. The strangeness continues, and that is perhaps the most wonderful thing of all. Take a moment tonight to step outside if you can. Look up at the sky. If you are in a dark place, away from city lights, you might see the Milky Way stretching overhead, a river of light composed of billions of stars too faint to see individually. Each of those stars has its own story, its own formation, its own eventual fate. Some of those points of light are not stars at all. They are galaxies, island universes containing hundreds of billions of stars each, so far away they appear as single points. The Andromeda Galaxy is visible to the naked eye as a faint smudge. Photons that left its stars more than 2 million years ago finally arriving at your eyes tonight. Between those points of light is darkness, but that darkness is not empty. It is full of dark matter exerting its gravitational pull. It contains rogue planets wandering without stars. It hums with gravitational waves from merging black holes you will never see. It glows faintly with the cosmic microwave background, the oldest light in the universe, older than any star or galaxy. Everything you see and everything you cannot see is connected. The same physics that governs atoms in your body governs neutron stars and black holes. The same elements forged in distant stars make up the ground beneath your feet. The same expansion of space that carries galaxies apart stretches the light on its way to your eyes. We live in a universe where strange things happen all the time, at scales too large or too small, or too fast or too slow for us to directly perceive. Supernovae explode, black holes merge, planets form, stars die, all continuing their ancient cosmic dance regardless of whether anyone is watching. But someone is watching. You are watching, and that matters. Consciousness, as far as we know, is rare in the universe. Most of the cosmos is dead matter following physical laws without awareness or understanding. Stars do not know they are shining. Black holes do not know they are swallowing light. Galaxies do not know they are spinning. But here, on this small planet, matter has organized itself into patterns complex enough to be aware. We know the stars are shining. We understand why black holes swallow light. We have mapped the spinning of galaxies. We have discovered the strangest things in space, and we have wondered at them. That wondering is precious. It is what we are for, in some sense. To be the universe's way of knowing itself. To take the raw facts of existence and turn them into understanding, into meaning, into wonder. So do not let the strangeness of the universe intimidate you. Let it inspire you. Let it remind you that reality is more than the everyday surface of things. Let it drive you to ask questions, to seek answers, to keep learning. The strangest discoveries in space are invitations from the cosmos. Invitations to participate in the grand project of understanding. Invitations to connect with something far larger than ourselves. Invitations to wonder. Accept those invitations. Follow the questions wherever they lead. Because at the very end of everything, after all the black holes have evaporated and the stars have burned out and the last atoms have drifted apart, what will have mattered most is that someone looked up at the sky and asked, why? You are that someone. This is your universe too, as strange and wonderful as it is.